Hi, hello everyone, and good afternoon. Long time. Wow, there's a lot of people today. Yeah. And well, as usual, we have here Aidan lecturing. Say hi and
hello everybody.
And our guest. It's an honor and a privilege to have here Tanmaya Mishra, a colleague of ours from University of Twente. So
yeah, not only colleague but also friend.
Yes, indeed.
I can say that we have been pushing him to give that presentation for more than a year. We've finally made it.
Finally, yes.
Well, shall we wait? I don't know, a couple of minutes. So if someone is a bit late, they can also join.
Yeah. So you're somewhere in a cold area, or what is it? Is it white in your outside? Is there snow outside of your window or not?
No, it's called white paint.
Okay.
But it's white as well. No, I mean, actually, I'm sitting in Barcelona.
Oh, okay. Yeah. So no snow for you.
No, for me, no. Yeah, better not. Every time it snows in Barcelona, it's kind of chaos. It's like end of the world. It's like the apocalypse. So, cool. So let's go. Well, as I mentioned, it's an honor to have here Tanmaya Mishra. Tanmaya Mishra is an assistant professor at the University of Twente, focusing on Geo-Tribology, I would say. When I had the pleasure to share office with him, he was only a tribologist, so now it's a geotribologist, which is like a
upgrade.
Higher level. It's upgrade, yeah.
Specific.
Well, what can I say? I'm a Tribos master, if I recall properly, the first generation. So the first generation of the Tribos master, that means being in Luleå, in Ljubljana, and in Leeds. Yeah, am I correct? Yeah.
Yes,
correct.
Exactly. The 3 L's. Yeah, as I said.
So the first generation of the Tribos master, and I think now it's 8 years now. Has been.
It's been 10 years. 2013 I started. So yeah.
Wow.
8 years of graduation, indeed. Yes.
You're getting old. And well, just to say, without further introduction, please, Tanmaya, the stage is yours.
Indeed. So I'll just start to share my screen. Right. I believe you are able to see the screen.
Yes, we are.
Yes. Okay. So good morning, good afternoon, and good evening, everyone. Depends where you are joining from. I am Tanmaya Mishra. As Chavi mentioned, I'm working in University of Twente as an assistant professor in the Surface Technology and Tribology chair. And I welcome you to today's presentation on tribology of earthquakes. Two topics which are randomly or not very often taken together. So I had this opportunity of working on this unique topic on tribology of earthquakes when I got the proposal granted with NWO program called DeepNL, which basically studies the subsurface in the Netherlands and all kinds of human activities in the subsurface, which results in subsidence or in seismicity. So this project is with DeepNL, and you can see here it's me and my PhD student Malek. We are in the lab, bit with seriously looking, with our equipment in the lab coats. Okay, so of course I mentioned I come from University of Twente. So basically, if you see here, we are in this small city called Enschede at the border of Germany. And this is a fun map. So if you basically have the chance of raising water level of the sea, then perhaps Netherlands, which is typically a low-lying country, will mostly be submerged under the seawater if you rise it above 13 meters. Well, we will be dry and safe here in Enschede. So a good place to be. And In our group, we have, of course, it's a tribology chair at University of Twente. So the chair is headed by Professor Matijn de Roy, and we are 4 assistant professors along with lab engineer who work on a lot of different topics which relate to interfaces. So we basically work on stationary to moving interfaces and interfaces which are sometimes stationary and sometimes moving. As you'll see, so we work on moving interfaces like bearings and seals, oil seals, which I think Chavi did his PhD about, and cam rollers, and also metal forming. And then we work on stationary interfaces like composites and hybrid materials. And then also we work on interfaces which sometimes stick, which are stationary and slip. So these transitioning interfaces, for example, fibers in lithography, positioning mechanisms, and earthquake. So through this, we have this chance of working a lot on friction, wear, and lubrication, typically studied in tribology, but also on topics like contact, bonding, and adhesion. And basically, these type of mechanisms are also studied in surfaces and degradation of interfaces. So it's a very diverse group with almost 15 plus PhDs and a lot of different research topics. And one of the research topics which we're going to focus today is earthquakes. And if we really think of it, earthquakes or prediction of earthquakes is something which has bothered mankind since a long time. And as you can see in this small animation here, basically this is a very old seismoscope which was developed in China, where basically if there was some kind of vibration, ball falls from the dragon's mouth to the mouth of a frog, and if the direction of the side of the seismoscope on which this incident happened, people thought an earthquake is coming from that side. Very rudimentary, but what you think of it, if you think of it, you can see how earthquake has been significant in making humans think why and how we can predict earthquakes. So this is an age-old question. Now, tribology is also a topic which has humans have been studying for quite some time, and this is one of the Egyptian wall paintings from one of these famous Egyptian tombs, which was discovered, which was designed back before Christ, few thousand years, about 4,000 years back. And what you can see here is a human which is pouring water in front of a sledge, which is dragged by several people. And what he's doing is he's basically playing the role of a tribologist, where he's able to change the coefficient of friction between the sand and the sledge, and solve this whole problem of all these workers who find it hard to drag this sledge by making it a bit easier. So tribological solutions have existed for a long time. And also the problem of prediction of earthquakes have also existed for a long time. And what we will see is how we can find a nice tribological solution to predicting earthquakes, or in fact, how tribology can play a role in prediction of earthquakes. Now, to see this, you need to understand why we have earthquakes. Now, typically in a lot of rocks underneath the earth, or in a lot of plate boundaries, where continental plates or oceanic plates, they are merging, or they kind of are diverging from each other, you have discontinuities in rocks, and these discontinuities in rocks are called faults. Now, for the scale size, if you see, these faults can span from meters to kilometers in length, and they're pretty big. So if over a period of time, these faults, they slip, and the friction in these faults reduce, that results in a slip event, which when manifested on the surface is what we called an what we call is as an earthquake. So the reduction or the change in friction in faults manifests as a slip event, and that manifests itself as vibrations on the surface of Earth, and that results in earthquake. And already you can appreciate and start thinking how friction is relevant for understanding earthquakes. Now, When we talk about faults, they come in different shapes and sizes. You see here continental faults, and these continental faults, what you see here is the San Andreas fault in California, which is a typical strike-slip continental fault where these faults move parallel to each other at a velocity of a few centimeters over 1 year. And also what you see here is that this is a subduction zone. And in a subduction zone, you ideally see an oceanic plate, which is penetrating below a continental plate. And as this happens, there is friction buildup at the interface of these plates. And then when the friction reduces, suddenly there is a sudden jerk event where there is a sudden slip, and that manifests itself as an earthquake, perhaps it results in tsunami. So you have faults across continents, you have faults across oceans, and these faults are vastly different in the way in which the structure of the rocks vary across these faults. So faults are complicated. And also you have subsurface activities. So humans, we've been trying to dig into the subsurface. And what we've done is we've done this for extraction of mineral resources. And with these subsurface activities, what that has resulted in is that we have reactivated pre-existing faults. And that reactivation of faults has induced seismicity. So fault reactivation by human activities can also result in seismicity apart from the natural movement of faults which occur because of the tectonic plate movement in a lot of continental and oceanic plate boundaries. Now, if you really see into the structure of a fault, and if you think of it, fault, of course, is at the discontinuity of two rocks, but over a period of time, these rocks, they move across or against one another, and they wear and deform and fracture and form these crushed rocks in between these two plate boundaries, which are called gouge. And these gouge are nothing but broken and crushed rocks, which form between two fault gouge, fault plane boundaries. And also, apart from having rocks in between them or gouge between them, there are also regions of contact where fault planes, they directly come in contact with one another, and these happens over asperities, direct contact of asperities between fault planes. And if you see what happens when these faults, they slip and slide, is that results in earthquake. But also, as for a lot of gas extraction which happens, as the gas is being extracted, the pressure of these gas on these rocks above it, that reduces. Now, because of this extra overburden pressure due to the reducing gas pressure, there is additional stress on these faults, which reactivates them. They start slipping. And as these faults and the reservoir rocks, they start slipping, there is ideally induced seismicity, but also there is subsidence, where the surface goes down from its natural plane. And there is also subsidence and compaction of the reservoir, and that results in subsidence of the field or the gas field. And these kind of problems are kind of very familiar in, very common in Netherlands, where you have the Groningen gas field, where gas extraction began in the 1960s. However, you see that there has been significant seismicity in the Groningen gas field beginning 1990s and early 2000. There was in fact one of the most significant seismic event in Huizinge where the earthquake of magnitude of 3.4 close to 4 Richter scale happened. So Groningen gas field, which is perhaps the 9th largest, at the beginning was the 9th largest gas field. You can see problems of seismicity, and also the gas field is going down. So there is also subsidence of this gas field. And this is resulting from the compaction of the reservoir, but also the slip and the sliding of faults. So this is a little bit about basically what faults are and how friction in faults affects these kind of surface effects. And before going further, I think it's interesting just to see what people think when we talk about these gas reservoirs. What does it come to their mind? And I think it's good if you can open WooClap and we can try to do some questions. But before that, I'll just talk a bit more about the Dutch subsurface. Where basically, apart from gas storage or gas extraction, the Dutch subsurface is also quite significant for storage of energy. Now, with the current energy transition, what is important is that the subsurface of the Netherlands, which is commonly has been used for gas extraction and also for salt mining, is also relevant for a lot of other storage applications. In future, for example, hydrogen and carbon dioxide will be stored, and particularly hydrogen will be stored and extracted to meet the changing energy demands during winter. And in order to store hydrogen, subsurface plays a crucial role where you can store and extract large quantities of hydrogen. And while you store these hydrogens, these depleted gas reservoirs, because the Groningen gas reservoir is quite depleted, is relevant for storing hydrogen and also for storing carbon dioxide in the North Sea of recently. And in these kind of storage activities also, it is highly possible that you can reactivate the fault and the reservoirs can also have subsidence. So not just for gas extraction or fluid extraction, understanding fault mechanics is also very important for storage applications and also for geothermal energy, where you also drill into the earth and you also extract hot water or pass hot water in order to produce geothermal energy. So this is a little bit about the Dutch subsurface and how it is relevant for energy production. But I think it's nice if we can look how well do we understand these reservoirs. And if you go to wooclap.com, it's curious to see what people think when we talk about a gas reservoir, what kind of structure comes to their mind. And I'll be curious if we can have some answers coming in.
Plug in. Or...
We have a couple more questions, but I think, just to see what people have an idea, because I had a lot of misconceptions when I started working on this project. So I'm sure people, might also.
Well, I mean, I don't know. Can you see how many people logged in, or?
Yes, I see some answers coming in.
All right.
We have most answers for porous rocks. Some people think also that it is hollow space between rocks. Some think that a gas reservoir is mainly porous rocks.
Can both of them be wrong?
It could be.
Okay.
No, it could. I think we'll wait for a few seconds before.
Yeah.
Okay, I think most of the people have answered this correctly. I used to think, I'll be honest, I used to think basically a reservoir is a hollow space between rocks. But ideally, a gas reservoir is nothing but porous rocks where the natural gas is stored between the porous media in the rocks. So most people, of course, know this correctly. I think if we go forward, there is also one more question. Is what do people think? What are the depths at which these gas reservoirs are located? So some people think, especially the Groningen gas reservoir, if people are from the Netherlands. So what are the depths at which these porous rocks, they have gas storage? Okay. No, not a lot of people think it is 12 kilometers deep. Okay. To be honest, actually, I think the deepest humans have ever dug is 12.2 kilometers. So I'm sure that is not for extracting gas. So most of the people are in that range. It is actually, for Groningen at least, it is 3 to 4 kilometers deep. So this is the depth at which you find the reservoir rock for where you find natural gas. And the last question, so we have a question on the length. Now we go to question on time. So when do you think the source rock for this natural gas was formed? So these gas, of course, are not just formed recently. They've been formed for quite some time. And when do people think was the rock which resulted in gas formation was formed? About 100 million years ago, we had dinosaurs roaming around the Earth. Billion years ago, we had few microorganisms. I think 300,000 years ago, we had humans already, early humans. Okay. A lot of people say it is 100 million years ago. So typically the gas is trapped in these sandstone porous rocks, but the gas is formed from shale, from organic matter, from carboniferous rocks. And these carboniferous rocks were formed in the Carboniferous era, which was about 300 million years ago. So at that time, Netherlands was located at the equator and it was filled with forests. And as these forests decomposed, it formed shale, and these were basically the source rock for all these gas which is formed. And of course, over millions of years, Netherlands drifted and came to the north and came to Europe. So the point of doing this is what we can see is when we talk about these faults and these rocks, we talk of time scales which are in the order of millions of years and length scales which are in the order of kilometers. So we are talking about pretty big time scales and length scales, and that is exactly the reason why it is so hard to predict earthquakes. Not just because they have long length scales and time scales of these phenomena, but also they consist of complex heterogeneous systems. There are not just rocks, but also gases and fluids which are present. These rocks have different mineralogy, and also these, especially for gas reservoirs, these are all closed systems. It's very hard to drill through faults particularly, so it's very hard to have a direct observations. You can have seismological data, you can also have some kind of drill hole data, but most of these drill bores are not through faults. And also lab scale simulation. So in an ideal world, if you want to study faults, you want to simulate them at the lab scale. And you want to do that at the same length and time scale, which is very challenging because we just see that these faults are formed over millions of years and they are formed over distances of few meters and kilometers. So replicating them at the lab is very difficult. And also the mechanics of fault, slip, and fractures, they vary from length scale to length scale. And the physics that is happening at the micro scale is very hard to understand directly. So what we see is that these challenges, because they make it so hard to predict earthquake, forecasting earthquake is almost the holy grail for geophysicists. It's one of the most important topics to for geophysicists to understand, and one of the most simplest studies in which you can understand earthquakes is by a spring block slider mechanism where your velocity or your dynamic friction is velocity dependent. So if you have a spring block slider and if you drag it, and if you see one of these experiments where you drag a spring block on a sandpaper with an elastic band, you see these elastic energy being stored, and then these friction, as if this elastic energy is overcome, there is a sudden slip motion. And this kind of replicates what happens in a fault is as these faults are deformed, there is elastic energy being stored, and then as they deform and slip, this release of elastic energy is through a sudden slip event, and as this friction is overcome. So this is even more complex because in reality, you do not have faults which just have one contact, but you have multiple contacts. And already if you couple two of these spring blocks here, you can see that the slip event or the stick slip behavior, as you see here, is not just very random and is not periodic, but it becomes a bit more random in this case, where these slip events are sort of coupled with one another. So one of the simplest ways of doing fault mechanics is by simulating it with a spring block, and I'll come to it a little bit later. But what you can see is that this is one of the initial ways of modeling faults. The other way in which you can, of course, study faults is by rate and state friction laws. So these are friction laws which are used a lot in fault mechanics, and these friction laws, they are mostly empirical. They lack a physical basis, and they also have different evolution laws. So that basically tells how the state or the contact area or the state varies with time. And the friction law, as you can see here, is velocity dependent. So the friction law depends on the velocity of slip. And also here you can see V star, but also it has different parameters, the rate and state friction parameters like A and B. And if you see how these friction evolves over the sliding distance, you can see if you change the velocity from V1 to V2, there is a sudden change in the friction instantaneously, and then it goes to a steady state value. And as you can see here, this sudden increase in the friction for an instantaneous change in velocity, it's called direct effect. The change in friction with time. So if you hold the body for quite some time, and then it is called time dependent friction. And also the change in friction coefficient with the change in steady state friction coefficient with different velocity results in a velocity dependent friction. Ideally, if your coefficient of friction reduces with increasing velocity, that results in a velocity weakening effect, which means that as your boundaries start to slip faster, the friction reduces, and that results in a very unstable stick slip behavior, which results eventually in earthquakes. If your velocity reduces and your friction increases, that results in a stable behavior. So most earthquakes result from the velocity weakening behavior, where friction reduces with velocity. And this happens over a sliding distance, which is called a critical slip distance. So the longer the slip distance is, it takes longer for the velocity to stabilize. And this critical slip distance is an important parameter in understanding the magnitude of earthquakes. So we can see here that there are friction models which are empirical, which are used to predict earthquakes. But then the basis of these parameters are not well known. And that is the reason why a lot of experiments are done for different types of rocks which are present in the reservoir and above the reservoir. So for example, in Groningen, the reservoir has sandstone, it has claystone, it has salt rocks, and also it has shale. And a lot of experiments are done in Utrecht University where large-scale rocks or large-scale rock samples are slid or rotated over one another. And this was done in one of the PhD theses at Utrecht, where different combinations of rocks or crushed rock gouges were sheared in a rotary shear apparatus. And basically the friction behavior of these rocks were studied with different velocities here. And you can see for most rocks, particularly for sandstone, it showed velocity weakening behavior, which means that when these faults, they are present and they are reactivated in these reservoirs, if these faults friction reduces, then it results in nucleation of earthquakes. But the problem with these kind of experiments is that these experiments are, of course, done in samples which are centimeter scale samples. And then these experiments include the combined effect of millions and millions of grains. And then it is important that how these experiments are scaled up to a fault which is few meters to kilometers in length. Now, also, the other way of modeling faults is that you use these rate and state parameters from a spring block slider model where you include the rate and state friction behavior as your friction law for a spring block slider. And then you model earthquake or the slip behavior in these faults as a spring block or a combination of different spring blocks. And then you model heterogeneity where you have different types of contact. So you have fault asperity contact or you have gouge layer contact as a combination of different friction behavior for different spring block combination. And by doing this, you can model fault heterogeneity as a combination of spring slider model. And then you can ultimately derive how the shear stress in these faults, they vary over the sliding distance and time, and how this velocity, as you can see, there is immediate stick slip behavior, and you see how this velocity varies with time. Now, you can, so for example, you do experiments, you can also do numerical models. What you can also do is you can have microphysical models where you basically have small scale grains, where you basically have gouge layer modeled as small grains. And then the friction or the grain boundary friction is modeled in these gouge layers from friction models. Although again, these friction models are theoretical. They do not have a physical basis to it. But then these form microphysical models, which are then incorporated in fault mechanics to model friction behavior of these large scale faults. So all these models, as you see, they rely on small scale friction, but they do it by doing theoretical models or by doing empirical models. And also, one of the ways in which you can also model fault friction is by doing numerical modeling by discrete element models. So you ideally represent a fault using a discrete element system. And this has been done also where you basically model a fault gouge as a discrete element set, and then you see how these fault gouges break, and then as your fault slides, how these changes. So what is important here is that you can see in all these cases how the behavior of individual grains are modeled numerically and are also modeled theoretically without basically studying into the actual physics of grain scale friction. And if you see here, this is how the scaling has been done up until now, where you have faults which are hundreds and meters of length, and these fault gouge, which are of the order of few centimeters. Now, this is what you see here is a Gutenberg Richter scale, which is typically shows how the probability of earthquake varies with magnitude. And this is from Groningen data, where you see that large earthquakes occur with smaller probability, and you see smaller earthquakes occurring with much larger probability. And this basically tells you what is the distribution of magnitude of earthquakes over the probability distribution of magnitude of earthquakes over different time frames. And you see the probability of larger earthquakes increasing with time as the production in Groningen increased. And this has been modeled by doing lab scale experiments on glass beads or gouges, where your lab scale gouge was sheared with a gouge of 1.5 centimeters. And that gives you also the frequency distribution of different events or stick slip events for different shear stress drops. So your magnitude of earthquake corresponds to the shear stress drop in these experiments. Now, what is missing here is that we really haven't investigated into what is happening between the contact between individual grains. And typically friction is predominant in the microscale contact, where the contact between individual gouge grains determine how the friction in all these millions of grains is determined. So this is a part which is not very well investigated until now. And as a part of our research here at Twente, we essentially model friction at microscale, which is the contact between individual gouge layers or gouge grains. And then we upscale it to large scale experiments, which is done in Utrecht. And by collaborating with them, we essentially upscale friction from microscale, and we aim to upscale it to the meter scale faults. So by combining knowledge of tribology and knowledge of geomechanics in this new field called Geo-Tribology, we want to upscale friction right from the micro scale up to the large scale faults. And to do this, we basically study these fault gouge as a combination of individual tribosystems, where we model individual contacts in our experimental setup. So we do experiments on individual grain-grain contact, and then we study the friction behavior in these contacts as individual tribosystems. So we take these contacts as individual tribosystems, and then we upscale friction in this single tribosystem to the tribosystem, which consists of millions of particles. So this we do in this so far has been done in the geophysics community, where they have done experiments on faults of centimeter scale. So they have created rock layers or gouge layers, which are a few centimeter scale, and they have tried to upscale it using numerical models up to the nature, where you have faults of kilometer scale. And by these numerical models, which include these rate and state friction law, they're able to see if these models can be validated at laboratory scale. And if so, then they can extrapolate and upscale it to the nature scale. Now, what we do is we use a similar method where we do experiments on individual grain on a flat surface. So we model or we do experiments on single grain, and then we put the friction behavior of a single grain into a friction behavior of millions of grains in these gouge layers. And then we see if these friction behavior, which is upscaled from single grain, can be effectively replicated in these gouge layers consisting of millions and millions of grains. And we do this by modeling friction in single grain contact, where we also do velocity, sudden change in velocity, where the velocity increases rapidly over a small time frame. And this sudden change in velocity is used to extrapolate the rate and state friction parameters. So we basically use rate and state friction parameters derived from single grain experiments. And then these rate and state friction parameters are incorporated in a numerical model. Now, this numerical model is based on the spring block slider model that you just saw. And these friction model that this numerical model uses is the rate and state friction law. And then this numerical model gives us the output for shear stress drop in the millions of gouge setup, basically, where we do experiments. So these experiments are coming from these gouge experiments in Utrecht, where we also have shear stress drops. And then we compare the shear stress drops in both the cases for different experimental conditions. And then we basically see how you have a similar trend in the shear stress drops for different humidities. So having done these experiments, we can see that it is possible to upscale friction from single grain to millions of grains at centimeter to decimeter scale. And then the trends in the friction behavior are comparable for different types of relative humidity. And through this, there are some initial confidence on which you can actually upscale friction from single grain to a scale of few centimeters or decimeters of gouge layer. So this is part of an ongoing research, an ongoing paper, and this was already presented in few conferences. And as you can see, the whole impact of this research is that by combining tribology with geophysics in this new field called Geo-Tribology, we will be able to actually constrain the prediction of the maximum magnitude of earthquake that can happen in a induced seismicity situation. So by able to upscale friction, we can able to predict the magnitude of the shear stress drops, which are nothing but the magnitude of induced seismicity. And we can tell or put a constraint on what will be these magnitude of induced seismicity for a given application running in. So this is the eventual impact which we aim to create with this research. and hopefully we will also we will have upcoming PhD vacancies which will be related to the topic of tribology and earthquakes. So I'm sure if there are people who find this topic challenging and interesting, they can of course write to us and contact us for a potential application. I thank you all for giving attention to this topic. And if you have questions, please feel free to ask.
Thank you, Tanmaya. Super interesting, actually. Yeah.
Thank you.
Fascinated. Yeah.
Guys, if you have questions, anybody in the audience, please write them in the chat or raise your hand and we'll unmute you and you can ask your question.
Oh, and on a small anecdote, this is me in between the fault which spans across the European plate and the North American plate in Iceland. So that's my fault. Yeah.
I feel like part of the audience. I have a question, Tanmaya, if you don't mind.
Yeah, sure.
And I'm going to be polite and I'm going to start. I'm very, well, I would say curious about the setup. So, I mean, how to replicate earthquakes in the lab. And there were some kind of two washers, no? Two kind of discs.
Yes.
You rotate some kind of pin on disc machine. Why this setup?
Right. So the advantage of having a setup like this, I think I can go to, so this is how it looks inside this setup. So you have this ring where you have these rock layers which are sandwiched in between. And these rock layers, they are sheared between the two rings. And the advantage of having a rotary setup is you can keep on going. So there is no limitation on the displacement that you have. There are also setups where you can just shear them parallelly. So these setups replicate how a fault core or a fault gouge slides, where you have two plate boundaries, which are these fault planes. And then as they shear, the grains, which are crushed rocks in between them, they are sheared and there is stick slip. So this replicates the shear of a fault gouge, essentially.
It happens in two contexts. You're actually testing two different contexts.
Here it's mostly testing the fault gouge contacts, these crushed grain contacts.
What velocity do you use? Because I mean, I can imagine it needs to be pretty slow. No?
Indeed. So we do at, I think, few microns. I think I did also experiments later, but we do at a velocity of 1 or 2 microns per second.
Oh,
so these are quite slow.
Interesting.
Yeah, which is at the velocity almost at which a fault moves.
And just to finish, loading wise?
So the loads which we apply here is, I think, pressure of 8 megapascals, which is the pressure of rocks. Yeah. So although the 8 megapascal is the nominal pressure, and the pressure between individual grains or the load results in almost few newtons.
Oh.
You have almost a grain of tens of layers of grains in this contact, and the thickness of the contact.
Amazing. I have a lot of questions, but I think there's someone else that has them.
Sure.
But
I wanted to ask you, Tanmaya, before anybody else. So for the modeling part, you went from the experimentally measured data to the fitting, and then to the upscaling. Is that the sequence?
So in between, I haven't showed. So basically, the experimental results that are outputted here, they are used to derive parameters like A minus P, which are rate and state friction parameters. Now these parameters are fed into a numerical model, a boundary element model, which basically replicates a spring block slider. And essentially this model takes parameters from experiments, and then it simulates a spring block sliding mechanism, and then it outputs the shear stress drops.
Okay. And so for this boundary element model, you use some surface input, or you assume surfaces to be flat?
Yeah, you assume like a 2D surface or a 1D surface if it's a single spring block slider, and you assume them to be flat. You can also do that with 3D surfaces, but then you need to have fault asperities and behavior where you assume each asperity contact as individual element, and then include the friction of each asperity, the friction parameter of each asperity in the model.
Okay. There is a question from the audience, Gus Molina. You can ask your question. You can unmute yourself and ask your question.
Hi, can you hear me?
Yes, I can.
Well, Gus Molina, Georgia Science University from the U.S. So my question is regarding prediction of occurrence of earthquakes. That I know is a big concern, not their magnitude. That I think that your work is a beautiful work in terms of their magnitude. This knowledge could be applied to the prediction of the occurrence of earthquakes, like an early sign.
Yeah. So this is really about predicting the magnitude, the maximum possible magnitude of earthquake, not as much as the timing of earthquake. So we are mostly focused on what will be the maximum possible magnitude of earthquake if you are given the parameters or the pressure in specifically in induced seismicity. If you have induced seismicity, what would be the magnitude of earthquake that is possible? So we are constraining that, not. So yeah, that is initial idea of the project actually.
Yeah, I'm asking that because years back, I did some work on tribo emission and tribo charging, and I know that there was some attempts to use that to predict earthquake in a way that well, it's been proved that before earthquakes there are sudden changes of the geomagnetic field, and
Indeed.
even the occurrence of lightning in in a clear day.
Exactly.
And that can happen hours before. That can happen hours before the earthquake.
Yeah.
So I wonder if you that I was never really put into practice, because of difficulty. But that tribo charging is probably a probe that could be used to predict.
Indeed.
I don't know how to connect to what you did, what you're doing.
Indeed, I have also read of these studies where you have a change in the magnetic field or the change in the surface charge because of, but yeah, I'm not sure if how well these studies are done or if these studies can really predict very well in advance of event of earthquake. They're probably predicting few minutes or few hours at best, but I'm not very aware of exactly the amount or the feasibility or the efficiency of these studies to be able to predict earthquakes way before in time, which is what is important. I think you would want to know at least few days before in time, right, to be able to take relevant actions.
Yeah, thanks for your answer. Anyway, your work is really relevant, and congratulate you in your in your research.
Thank you.
So with that model, Tanmaya, you will be able to predict the magnitude of the earthquakes for this
Groningen field.
Groningen field.
Yeah. I mean, if you the advantage of doing a physics-based model is you can learn from Groningen data, so you can validate it with models data from Groningen gas field. And if you understand the physics of the friction which causes these events, then you can also extrapolate it to a lot of other applications where you have induced seismicity from maybe drilling or maybe geothermal drilling or storage of hydrogen. So we'll use it. You'll use the data of Groningen to validate our model finally at the field scale. But then if you've, since we are doing upscaling from micro scale, and hopefully if you understand the physics well, you can also use the model more globally for any kind of induced seismicity if you know the type of rocks which you are drilling through, working with. But yeah, that is of course far-fetched. Hopefully we'll be able to achieve that. Fingers crossed. Yeah.
Good question, because this thing in Groningen, from what I read on the news, it's about there was fracking, no? The fracking, they were using this practice to extract natural gas, was it?
Yes, I'm not sure if it was fracking though.
Okay.
Oh, no, isn't fracking for oil? I don't know. Correct me if I'm wrong. I'm not also an
No, no.
expert on the.
I read it on the news. I've been there. So
Yeah.
there were many people saying that this activity and the earthquakes were not correlated, or they were correlated. I don't know if it's a very political question, but I don't know. Is it something that you could foresee in your model, or what is the impact of? Yeah, good.
I mean, the
I
thing with
think the issue was there that there was a damage to the houses of people. I think that was
yes, cracking. Yeah. So in Groningen, a lot of
problem.
houses are cracked because of constant. You see a lot of small earthquakes happening, although on surface you might not feel okay. Earthquake of magnitude 2 or 3, it's not very dangerous or cannot collapse a building. But if it happens almost every 2 days, frequently through the whole year, then you will have cracks and the houses become very damage prone, let's say. And in Groningen, a lot of villages in that Groningen region have houses which are quite cracked, which are very, let's say, precarious to live in. And I don't know about right now extraction of gas, but I think the extraction of gas in Groningen, if I'm not wrong, will be terminated by 2025. And that's exactly because of this reason, is that there is so much of nuisance because of the seismicity. And it doesn't mean always that termination of gas extraction will also result in a termination of subsidence or in termination of seismicity.
Right.
So because there will always be some kind of creep in the rocks, or you never know how the rocks will behave. So that's why also it's important to understand the physics of what causes this friction reduction. If you do understand, you'll be able to sort of help or decide if really stopping gas production will stop earthquakes.
Yeah, I've read somewhere about these earthquakes that the water actually now I forgot whether it facilitates or actually blocks the earthquakes, but there were some studies about that.
Yeah, that's the reason I think we also did experiments with different relative humidity. So I think I was showing this to you. We were doing experiments with different relative humidities, and you see how humidity is affecting the shear stress drops. So I think we do experiments with different relative humidity, and then you see the change in shear stress drops, and that is where also the presence of these water or pore fluid in the subsurface is critical in determining the seismic behavior.
Actually, I was wondering about that with one of your questions, no? With because we're talking about Groningen, it's like, well, we are under the sea level, so is there water there as well?
No, that is a hypothetical scenario. If you increase the water table by 13 meters.
No, yeah, but I mean the reservoir is underground.
Yeah, the reservoir is underground, but the seawater is above that height. So
that's height, okay.
Yeah, a lot of oil sea wells are also below the sea, but they are still having rocks above. So it's not that they are really exposed to the seawater. They are very well sealed off. So a lot of gas fields, they have salt rocks on top of the reservoir, and salt is a very good sealant, Chavi. You might also appreciate, because it's a natural seal, like rubber is an artificial seal. Salt is a very good natural seal. So
thank you.
They seal things very well.
Oh, okay. Didn't know that. Okay, wow.
Yeah.
Okay.
I see that there are no more questions coming from our audience right now. I think it's a very unknown field, actually. That's well. If in tribology normally it feels a bit alone, because in Geo-Tribology it's even more lonely.
Yeah.
So,
yeah, but that's the fun of it. That's the interesting part of it.
So there is a lot of stuff to do, right?
Yeah, there's a lot to do there.
Well, Molina again. I can tell you that to me, as a tribologist, interesting enough to make it part of my graduate tribology class. I plan to use your work. You know, if you agree with that, show some of the slides and stuff, it's possible.
Definitely.
Okay, thank you.
Yeah, thank you.
Thank you.
With that, I think we should close the presentation. Oh, I would say, Tanmaya, either something else to add?
No,
No,
just thank you, everybody. Thank you, Tanmaya. So
Yes.
maybe if there are questions or yeah,
I can
Some-
write my email. I think people can reach out to me on my email if they have questions. I think you will probably email is probably shared on the advertisement or no?
depends on you.
Yeah, but yeah, of
Yeah.
course, you can put that on the.
Yeah, you're
yeah.
not
sure.
afraid of stalkers, no? Good.
More importantly, if people are interested, I think someone is raising a hand. I don't know. I see someone.
Oh, yeah, true, correct.
All right.
and,
Yeah, just
from
a second.
Singapore. Wow. Please go on.
Raj, I think you can unmute yourself and ask a question.
Hello, good afternoon.
Yeah, hello. Good afternoon.
I am Raj from AGS Singapore.
Hi.
Okay, I'm really very impressed with your presentation.
Thank you.
It is a different perspective as compared to metallurgical and tribological of we are doing. But you are telling the microstructure and all. Normally materials like metals or non-metals you will do by scanning whatever the microscope. How you are checking the microstructure on the rocks?
Right. So after these gouge experiments, also we can look, or even single grain, we do look into a confocal microscope to see if there are any cracks which are formed on these rocks or in these grains. And we can also look into
What type of
scanning
microscope? What type of microscope?
a confocal microscope, which can check the surface roughness or the surface changes in the gouge. A confocal.
But it will give any microstructure or surface roughness.
So it looks into the surface roughness change and also if there are scratch marks on the surface.
Okay.
And also if there are cracks on the surface, also it can look into the surface cracks which are being formed.
So it will give a indication that there is a possible sliding or movement possible like that. That is the identification. Okay. Then what you are telling size, single grain size, where it is want to check the size of the grain. What is the
So those grain sizes, we can of course also check on a microscope what is the size of the grains, and the grain size that I typically use in my experiments are, I think, of the size of, so the diameter, because these are spherical grains. So the diameter of the grain is 400 to 500 micron of one individual grain.
Okay. The size, it is irregular shape. How you will measure? It is the particle is irregular or a circular one?
They are spherical particles. We can order spherical size grains of these rocks, especially if there are single mineral rocks like quartz. You can have spherical particle, where you have, they are quite
You will
regular.
take average diameter.
No, they're quite regular. You can order crystals which are quite regular size. So you can have, we have ordered samples and specimens where the grain size or the tip of the grain is of the size of the grains are very regular. They are not even average. There is almost 10% change in the size of the grain or error. So they're quite regular grains.
Oh, these grains, what is the part of the rock or where it is these particles coming from?
So for example, these rocks in the reservoir are sandstone rocks, and these rocks mostly consist of quartz crystals or quartz mineral, and 60% of the sandstone rock is mainly consisting of quartz. So our experiments which we do is mostly with quartz. And quartz crystals rocks you can easily obtain from the market where the size of the grain is fixed. So
okay, thank you very much.
And
one more thing, in metallic items, based on the lubrication regime, we can apply the lubricant selection and other thing we can do. But this type of whatever the boundary lubrication or this type of lubrication, how a lubricant you can apply, or to avoid such a friction, what type of feature we can do to avoid this type of friction creating heat as well as type of explosions? Is there any lubricant used or kind of?
That's a very interesting question. So this is under the surface of Earth, so you hardly have any control on the water media or the lubricant which is present. So you really cannot change the material which is, or the, because the only lubricant which is present or the liquid is water. And water is the only thing that is affecting the interface between the grains. So unfortunately, we cannot interfere, we cannot pump any lubricant inside of the earth, but we just have to understand what is happening, what is there, and only water is present in between these rocks, and we have to only understand how water changes the friction, but we cannot basically interfere by adding any lubricant.
Water cooled lubricant itself you see, but one small my doubt, maybe layman doubt, if it is a gas inside, which is flash point is less than 100 degrees or 75 degree, then when a small rock and another rock sliding or friction, whether there is a self auto ignition or a self flash point, this gas create and explode the two rocks, because in between the porous or whatever the crystals, there may be likely about 2-3 kilometers down gases, explosive gas or like LPG or natural gas, which have low flash point. So if it is low flash point, due to the movement of rocks, friction is created. So you are making a fire triangle there. So there is a gas, there is a auto ignition temperature reaching, means flash point, and there is a friction, it is heat.
Yeah, I can imagine you're saying if frictional heating causes the gas to ignite by some reason. Yeah, I mean, I don't think so. So probably you also need an oxidizing environment also for, and this is, you don't find that you have a very oxidizing environment under the surface. And also the friction values which are obtained are not that high enough to result in heat temperatures which are high enough to ignite the gas, I think. So to my knowledge, natural gas at least is quite safe. I know that with hydrogen, it's more possible to have explosion, but I'm not sure if that is because of friction, but that is mostly when there is leakage. If things are, the gas is very well sealed. So typically I haven't heard, or I don't see if friction can cause ignition of the gas.
So the explosion,
quite well sealed.
so last one question only, sorry. The explosion happening or some the bombardment from the bottom of the earth coming due to this reason, due to this explosion or earthquake coming due to these gases, that is flashable gases or flash point low gases like LPG or natural gas, is due to heat and due to that reason, because of the pressure directly proportional to temperature rising and exploding?
No, I don't think it explodes inside of the earth. This shaking movement happens because of fracture and slip. So the sudden earthquakes particularly happens because there is a rapid fracture or slip of these faults, but there is no explosion which happens in this natural gas which is present, because it's not a very oxidizing environment. Natural gas is mostly present as a phase in combination with water. So it's a phase where there is no oxygen, or very few, less oxygen at least. And so the oxygen is, you have to have oxygen to have ignition. And I don't think it's mostly water, natural gas, and rock. So it's a three-phase media. That's it.
Okay, thank you, sir. I learned a lot of new things from rocks.
Yes.
And thank you very much for your kind courtesy to explain me very detailed. Thank you very much to all of you. Thank you very much.
Thank you. Thank you.
Well, actually, thanks for your question. Interesting. I could continue. Well, I will continue next week with you.
When we meet next week, we can have,
Totally. Looking forward to it. Just thank you, Tanmaya. If you send us your address, we will send you souvenir. Actually, we know where you live, so that's good. So you will get a present from us. Thanks for that, and thanks everyone for joining. I think you were the last presenter of this year, if I'm not wrong, either, or maybe we have. Okay, but yeah.
No.
So I like to close things in a nice way. So thanks, Tanmaya, for that. We keep in touch. Thanks, everyone.
Yes. Bye.
Have a good day. Ciao.
Thank you, everybody. Yeah.
Thank you.
Thank you. Bye bye, guys.